Hello, folks, and welcome to Iron Beetle, a show where normally what we do is that we do programming. You know, we read the code, we discuss the code, sometimes we write the code, sometimes we draw some diagrams to explain how the code works. And the context for that is like Tiger the modern database for financial accounting implemented in Zeek without dynamic memory allocation, yada, 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 yada. But today, today we are going to do something different. It's not going to be code. It is going to be hacking. It is going to be like, pure magic. It's going to be like completely unhinged, crazy things. Because we are going to talk about upgrades. Okay, so upgrades. Let's remove what we've been chatting about last time. So as a reminder, I think we've covered everything we wanted to cover, but we basically explained the infrastructure between our fuzzing, which is completely unrelated. So today we have, well, actually, I'll just keep the canvas. The new topic, which is upgrades. Upgrades. And it is, it should be like bloody red because upgrades are always horrible. So what is the idea? Upgrade is simple, right? Like you have like your software, and let's say it's like green, and it is like version like 0.25, because obviously you aren't going to release software version 1.0, like no one is doing that. And then you do like small incremental upgrade. I don't know, maybe you decided that, hey, you like the cover blue better, and then you do like version 26. Like sounds like, super simple, super trivial. You just like apply the change, slap a new version number, and you're done. Well, that's not actually that easy, because software is used by people and software is used by other programs. And that means that software, like, generally has like some kind of an interface. I don't know how you would display interface. I don't know. Let's okay. I'm super bad at that. But let's say we have like interface like a socket which you could plug into into the wall or something. Like this is the interface. Okay, that's super confusing. Let's say interface. It is kind of like, I mean, it does look like a face, so that's why it's called interface. And now, like, you do upgrade. And okay, so also, like, this is real software, so real software has the user. So here is our happy user, and our happy user, of course, I'm super bad at that. Of course, cares a lot about the interface. Like this, like our user uses our software through the interface, and they are like very accustomed to this. So what happens if we release a new version of a software and we keep interface the same? Well, I mean, our user remains the same, like, because from the perspective of a user, nothing actually changed. Maybe the software became faster, maybe the software acquired some new features, but the interface that was exposed to the user before is still there, and the user is happy. But what if you make a mistake? What if suddenly your interface is slightly different? Well, the user becomes mightily upset in this case, because well, the user's use case broke. And okay, if the user is a human, or maybe, I don't know, large language model, they can adapt to the interface. They kind of like can see what was there before, what was there after, and they just they will be grumpy for a while, but they'll change their workflow, and it will be good. But if this user is actually a robot, so this is like another program with like a robot antenna, then that becomes super horrible, because programs cannot like automatically fix errors, so that leads to breakage. And that is kind of like the core trick when you are maintaining software which is developed over time. When you are building software which releases the new versions, is that you need to keep your interfaces compatible. It doesn't mean that you never change anything. You could implement non-functional features, like, again, making your software faster, smaller, more efficient. You could also implement backwards compatible extensions to the interface. Like you could add new features, you could add new use cases, but you aren't allowed to break stuff. Okay, so it seems like the problem with interfaces and with upgrades becomes easy, in that interface actually is usually relatively small part of the overall software. So you see, it's actually like not drawn to scale. Interface is like relatively tiny. So just maintaining this part through careful engineering practices should be possible, right? Well, kind of right, but also historically, no. Like there aren't going to be like breaking changes, and you need to realize like how you communicate that, how you discover that after the fact, and how you deal with them, which is like part of the problem. The bigger problem is that for Tiger Beetle specifically, our interface is actually gigantic. For Tiger Beetle specifically, our interface, or at least that part that is responsible, that part that we cannot break during upgrades, is actually pretty huge. So why is that? And that is due to determinism. So determinism, and kind of like usually we love determinism, but actually, and usually it's not hard to achieve determinism, but for upgrades, determinism is is something that requires explicit effort to maintain. Okay, so here I will need to take a sip of tea and then go back way back to, I think, autumn of 2024, where we were discussing compaction and repair on our stream. So hopefully you remember that Tiger is a cluster of usually 6 replicas. And what is unusual about Tiger cluster is that replicas need to be fully deterministic. So let me explain it. So okay, let's say we store some data, like a. Oh dear, I have super large scale. Let's go back to 100. Okay, so we have some data in our system which says, okay, A equals 1, B equals 3, C equals 92, D equals, I don't know, 100. Like, data, logical data. Well, let's imagine that physically we store this data as a tree, like binary search tree. So here we have our B, and then to the left stuff which is smaller. So it is going to be A here, and then I don't know, let's say D here, and then C is to the left of D. Okay, so like you could imagine that like this tree stores this data. So here we have 1, 4, 192. But the same structure could actually be represented by a tree of a different shape. So here we have another binary search tree. Okay, let's say that we now put D to the root. Now B is here, and okay, now where do I put A? So A to the left of B, to the left it should go. So actually it's going to be okay, something like this. So you see, the same logical data, A, B, C, D, but it can be stored physically in an abstract system like differently in 2 different binary trees. Why is this important for Tiger? Well, because let's go back to our crazy small scale. Because in Tiger we actually require, due to our repair protocol, that all of the nodes are exactly physically identical. So you couldn't you couldn't have like a situation, I don't know, let's say that this is like, slightly different node. Like this is completely unacceptable. Even if it stores the same data logically, if the data is different, represented differently on a physical level, that would be incorrect. Well, why is that? Because Tiger recovers from disk failures. So if this like green node has a particular grid block somewhere, and this like, okay, let's say this is the block with like address 16. Yeah. And let's say this block is red because there is some kind of like corruption there, like, I don't actually physically erase it, but you get the idea. So like, something, um, something's correct happening with the block, like, there is like some scratch or whatever, like the data isn't there. Well, the way this works is that this node is going to ask a different node. Give me block R16. I should put double D here as well. And because we guarantee that, or at least we strive to guarantee that the data is physically identical between machines, this node can say, okay, yeah, I do have exactly the same block. And here it is. And then the original node just like overrides it and fixes the problem. But now, what happens if we have a node with different physical structure? So if that request goes to this node, okay. If this request goes to this node, then we kind of like get completely different block. And actually, it is not repaired. And okay, if just one node is slightly different, that might be okay. But like, if they all are different, that it might be the case that this disk failure is simply unrecoverable. And that's going to be pretty horrible. Because, well, Tiger promises that it should recover from disk failures, and we are not recovering here. So we do have this requirement that nodes not only maintain the same logical data, so not only this middle part here is the same, we actually require that the left part and the right part are also identical on a physical level. How that ties to the upgrade? Well, okay. Let's say we implemented optimization in the compaction algorithm, which reduces space amplification. So let's say, like, before we had compaction, which wanted to merge, some tables from level A and some tables from level B, and maybe like in one version we decided that we are going to select these blocks for merging. But then we realized that, hey, we have a wrong heuristic for determine what are we going to merge, and in our next version we actually decide to select these two blocks for compaction. Well, that means that from this point on, there will be divergence in the data, and this will break our repair protocol. Like this picture would not be working at all, and that's like superset. Because I kind of was talking about this physical repair as a constraint, like, hey, we require physical repair and that's why we cannot do upgrades easily, but actually it is not a constraint. It is a major simplification because this repair protocol is like super simple. It works without database being aware of the logical data structures. So even if we, I don't know, replace our LSM trees and replace them with B trees, like you could still reuse our repair. This repair also gives us state sync for free. It allows us to have very strong guarantee of consistency of the data because everything ends up hash chaining up to the super block root node. So this is good. But like this is bad, because if we kind of like guarantee that we want to preserve the determinism, then we can't really like change anything about our code, because almost any change is going to affect the data layout on disk and is going to break determinism, and that's going to be super painful, super horrible, even if our public interface stays the same. So kind of like, this interface here is the same, but there is some like smudge, some difference there, and kind of like this kills us. So this is going to be super sad. Okay, what is the solution? The solution is crazy, like really crazy. Like it is like the best instance of systems programming design I've ever seen. Okay, so the idea is this: we acknowledge and expect that different versions of Tagevital will be behaving differently. That you wouldn't be able to run a cluster where half of machines are on version X and half of machines are on version X plus 1, like just now. That's not the case. So we kind of like have to maintain the invariant that everyone talks only to the same version. And it kind of like might seem that that's like easy. So like you run this cluster, then at some point you shut down all the nodes, upgrade them, and then restart. And that's kind of like, okay, that's not like fully available because you have downtime during upgrades. But at least you have like coordinated the upgrade, so you maintain the invariant that all the nodes are on the same version. But no, this will not work, because this is a distributed system. And although the nodes converge to the same state, there is no guarantee that at any given point in time they are at the same state. So when you shut down the node, it might be the case that this node is at op 99 too big. Okay, and this one here is 98, and this one here is 97, and let's say this one like is also 99. So but you get the idea, like those are different. So we'll get a picture where like, okay, op 99 was executed by 0 24 on replica 1 and by 0 25 on R2. So this is R1, this is R2. And that is bad because, well, this is precisely the problem we want to avoid. So that is the key invariant that we want to maintain here. We want to ensure that every single op is executed by the same Tagevital version. So essentially, we want to map each op to a version of target which executes its op. And like no other target version can ever try to execute this. We want to like coordinate upgrades around the cluster so that we do not end up in a situation where half of the machines are on the new target, half of the machines are on the old target, and they can't like, get unstuck. And we need to take into account the fact that at any given point in time, machines probably aren't at the same operation. So they are like slightly different. Some are slightly ahead, some are slightly behind. But like that slightly kills us. So okay, how do we do that? And that's crazy, like super crazy. There are like two components there. One is the crazy systems programming trick. We actually go and we pack in the same binary several versions of target. So if this is your target.exe, internally, it is actually like concatenation of several binaries. So it's going to be like target.exe v24, and then target.exe v25, target.exe v26, etc. So I will show you more later, but basically, let's try to build this. Where is version release? I think it's called release. Yeah. So let's try the config release. The config release, maybe it is spelled this way. The release client main. Okay, we'll get to client releases as well. Release client main. Okay, because I think it's also config. Okay, just so like we start looking at how this is implemented just a little bit. This will it will take some time to target 0 1.0. So let's see target version. Okay, yeah, it is. And then let's say we like change something. Like let's pretend that I like hyped for a week furiously. Build a second version. Just a second. Okay, and what we are doing is really this thing. So I'm wondering, is it actually executable? Okay, yeah, you see, it is actually executable. And I guess if we do it in the opposite way, we get, yeah, the second version. And it is twice the large. Okay, so I mean, it is not exactly what we do here. We actually do something arguably even more horrible, but you get the idea. We prepare this multi-version binary, which actually contains several versions of a target. And that means that this wide binary is actually capable of executing any of these versions packed. So in other words, we have this data file. And in the data file, there is a record that, hey, we've processed this number of ops. So let's say that we have like this data file, we have log like, op 10 was processed by version 0.17. And then op 11 was also 17, but then maybe op 12 is 18. And like op 14 is like 19. So we have this like in the data file, actual file on disk somewhere. When target-able, can I draw a target-able? Okay, I tried. So when target-able reads this data file, he starts executing at version 0.17 for op 10 and op 11. But when it goes to op 18, it realizes, well, okay, I wanted this to be op. So the last op was 11, for which we executed version. So, okay, this is op on the target-able, and here is the 0.17. Okay, so this is 0.17 target-able. When it sees the next op, when it sees op 18, it kind of like realizes that, hey, actually, behind me in the multi-binary, there is next target-able with version 0.18. So it goes, and then it like takes this op, but this op, it like handles to this UI binary, which exists in the same, again, in the same file on disk, because they are actually concatenated. Okay, so that's kind of like the first part of craziness. The second part of craziness is the support in the protocol for this. And it's actually, well, it is kind of like complicated, but also not really complicated. But basically, the idea there is that replicas communicate which versions are packed into their binary. And like, say, like everyone is on version 0.17. And everything is fine, like, everyone's on 0.17. Then what the operator does is that it drops a new binary on disk, which contains 0.18, but it also still contains 0.17. So that binary starts, it looks at the data file, it sees that data file still says that it should be 0.17. So, okay, it restarts as 0.17, but it kind of like has this mental note that, hey, actually, there is a newer version of target-able in my binary. and it starts advertising that to other replicas in the cluster. When the primary realizes that, hey, actually everyone in the cluster has this new binary, what the primary does is that it injects the operation to actually do the upgrade. The primary says, okay, folks, we are doing upgrade now, and the next operation is going to be 0.18. So the replicas apply this operation, and then they realize, hey, actually, okay, so now my data file tells me that I should be 0.18. And at that point, they go and restart into 0.18. Okay, so that is the whole story in pictures of targetable upgrade procedure. So let's quickly recap. So fundamental problem is that when you are upgrading software, you should keep your interfaces intact. And that is a very hard problem, but it is kind of like solvable if your interface is not too large. The problem with targetable, though, is that we require not only interface compatibility between different versions, we actually require that the data files are physically bit for bit identical, because we rely on full determinism for our repair. And that means that some trivial refactors, some trivial changes, some trivial optimizations, which do not affect our public API in any way, can break this determinism and can prevent our update. The way we combat this is that we maintain a strict invariant, that every operation that targetable is executing is going to get executed by exactly the same binary on any replica in the cluster. If replica 1 executed operation number 2 at version X, then replica 3 will execute that operation number 2 also at version X. It cannot execute it at a higher version, it cannot execute it at lower version. Okay. This isn't a full solution, because in cluster, actually, different replicas might be on different operations. So you cannot just like atomically upgrade everyone. This is a distributed system. So the way we do this is that we make sure that every targetable binary is actually capable of executing operations under several versions of a binary, because our binary is literally concatenation of multiple versions. And then there is extra logic, which says, hey, if I'm version X, if I'm version Y, and I am to execute operation number 2, but actually I know that operation number 2 should be executed by version number Y, I'm going to crash and restart into version Y. And finally, there is consensus protocol which coordinates the upgrade process itself, which waits until every replica in the cluster has this new binary in its pack, and afterwards it goes and says, okay, so from the next operation, we are going to do the upgrade. So I think we need to cover 3 things to fully understand the upgrade process. Well, maybe more, but at least 3. One is how we actually build this binary, like how we do this concatenation in the build system. The second question is how we execute ourselves at runtime. So like, okay, we have like this binary, which is concatenation, and we know that it can run, but how do we like re-execute into a different version if we chose to do so? And finally, the protocol parts behind the upgrade. So we obviously aren't going to cover all three today, and I think we'll need at least 3 episodes to cover upgrades. It is a lot of ground to cover. So maybe let's actually keep this episode to this high-level story, and let's look at the interface for producing the binaries. So like the build system parts. Okay, let me sit down for a moment because we'll be typing something. Actually, I don't really remember how we do this. But well, I mean, we could just try. Well, not TagBuild. So this is how we normally build TagBuild, just zig build. Okay. This is how we build, well, okay, before I do this, so if we just build a TagBuild, it says that it is 0.01, which is like development version. Like this is not production, definitely. Okay, we can set a configuration version, which says, hey, we are now version number 20. Now, I think there should be an option to, oh, oops, I think I want to flip this to dark mode. Okay, sorry about that. Okay, so I think there is multi-version. We have multi-version file. I don't blame. Okay, cool. Well, okay, I think we can actually cook this manually. Let's try this. So let's see build version 20 and cp zig out bin TagBuild 0.20, which is instant because everything is cached thanks to zig build system. Then we build version 21, which is like exactly the same, except that and now we actually okay yeah, I think this works differently. So we are going to build version 21, but we'll ask the multi-version file to include TagBuild. And I think this won't work because, or maybe it will. Okay, yeah, because macOS adds extra trick there, because for macOS what we actually do is that we include not only each version, but for each version we include 2 binaries for 2 architectures, for x86 and for ARM. So let's do this, but for Linux. Target x86, 64, Linux. Now we shouldn't be able to run it because, yeah, could not be run by operating system. Okay, and now if we say multiversion, but we still want to say that it is still x86 64, now it should work. Okay, it doesn't work. Why doesn't it work? It should work. Well, okay. Anyway, I've never used this version, so let's do something different. Let's try to produce a real multi-version binary. Okay, it would be embarrassing if it doesn't work. Well, we'll debug this. So normally the way you include multi-version binary is that you include previous release binary. Okay, so and let's try to build this host. And well, now that we use 16.0.48, we need to pick a reasonable version. Oh, I think 0.20 would also work. Okay, let's see. Aha. So we have our tag middle, and it is 39. But if we ask for verbose version, it says, yeah, you see, it says, hey, I actually know, I have actually two versions bundled. 0.16.48 and 0.16.49. So, okay, let's maybe try to do this. So we have tagbidal format, replica count 1. Let's format, and then let's start. Okay, so we see that we started with version 0.1649. Now, what I'm going to do is that I'm going to go to tagbidal's releases page, and we really should have our own releases. I used 48, right? Okay, so I'm going to download tagbidal universal Mac. While you're looking at this nice picture, this is the story. So we were in Amsterdam a couple of weeks ago on Systems Distributed Conference. Stay tuned for recordings of the talks, which I think are going to be streamed starting from next Monday. And like, you know, there was a party on like some high rise, whatever, with like a beautiful view onto the river. And on that river, like, you know, there's like a lot of like boat houses in Amsterdam where, like, you know, someone just like lives on the boat. So there's like windows and like toilets and like whatever. And it's normal. But what we saw is like, you know, like normal house, like, you know, it's not a boat house. It is just like a house with like, you know, which looks like a house, like, you know, roof and like kind of like not entirely like rectangular shape, like this like door, this like thing in front of the door. And that house was towed by a boat. So super hilarious. Anyway, we have tagbidal. Okay, is it it? file. Okay, it is. So it's just that macOS doesn't allow me to run things. Okay, so let's move this to Tagebital 0.16.48. Okay, Tagebital format. So now we format a data file using this old thing, and well, it doesn't work because okay, mv Tagebital 0.16.40. So this file was created by Tagebital version 49, and it hasn't actually logged that, which is not really cool. We should add that log. Okay. So, and this one is 0.16.48. Okay, so now let's see, Tagebitals start. So if we start our multi-binary Tagebital with the new data file, it says, okay, I'm version 49, Superblog version 49, all good, I have started. If we give it an old data file, you see, it opens the data file, it reads the release like itself, okay, so we are 49, and then it reads the release from the super file, from the superblog, from the data file, and realizes, hey, we actually have to transition to the previous release. So wait, why does it happen? Oh, okay. Okay. It surprised me. So, okay. First open, new Tagebital opens old data file. Notice that the data file is old and re-execs in the old version. Old version. Opens the data file. Notices that it is old version, but that it has actually a newer version available. Opens the data file, but then we are running a cluster of one. So this replica realizes that, hey, actually, like, we can upgrade the cluster because the cluster is me and I have the newer version. So it then goes and upgrades the data file somewhere. Do we upgrade in a release? And then re-execs again in the newer version. And then we open data file again. And now this data file is stamped with the new version. And like, okay, now we are done. So if we open this data file again, then we'll see that, hey, you know, we just so it's not, now it's misleading. It is called 0.16.48, but actually in the data file, the release is already 39. And if we try to pass the old, now if we try to open this data file with the old Tagebital, yeah, it said that, hey, kind of like, a release is not available, like upgrade or downgrade the binary as expected. So, okay, that I think is a good place to stop. I kind of like showed you this horrible magic of like dynamically switching versions. I'm kind of like, I showed you a magic trick. I haven't shown you how it works, like, like all the smokes and mirrors to make it possible. And that's going to be like a long story for at least 3 episodes, I think. But I hope you did enjoy this. And see you next time at 5 p.m. UTC, live on Twitch next Thursday, and after that on YouTube in recording. And actually, if you really cannot live with me for an entire week, I think that on Monday we start streaming videos from System Distributed Conference, and the first video is probably mine. So if you miss me, then please check out Tagabital's YouTube channel for some System Distributed stuff. Although now I realize that probably this video will be available on YouTube after Monday. So, okay, maybe this video is already there. So if you are on Tagabital's YouTube channel, then please go right now and check if there are some treats from SD25. Okay, time for our awesome auto track. Thank you.